Hello everyone, this is the video lecture for Calculus 3, section 16.2, line integrals. This lecture is very integral to knowing the rest of chapter 16. Ha, ha, ha. Okay. A line integral is really kind of interesting. I'm going to try to draw kind of a representation of what you could imagine it as. So, say that we have this kind of like curve going on between 2 points in space, and like this is a point P, this is a point Q, and this is a curve C. And what a line integral would be is kind of like the area underneath the curve. If you were to see this curve on the XY plane, so as a shadow in a way. So all this area beneath the curve, essentially, that would be your line integral. So this is useful in a lot of little things, but in particular, like application-wise, mass of a wire, perhaps. That's, I think, one particular problem coming up later. And it's also going to be used in other ways, not just for this application, but later we're going to be seeing it again pop up throughout chapter 16. So, one last thing is that it's not an arc length. I had to learn that myself. It is not an arc length. Okay. So let me first give you a formula, I suppose you can say. We got integral of a curve of f of x y ds is equal to integral from a to b of f of x of t, y of t, and then now times the square root of x prime squared plus y prime squared dt. Now, this might seem a little complicated. It's really not. Most of the time it works out pretty nicely. What's going on is that we have to make a parametric function, a set of functions, a parametric set of equations that will go inside of this f of x. So notice that we're taking our x's and y's and making them into t's, essentially. But when you do that, you also have to do this new change thing. You recall that we've done arc length. This is an arc length type of formula, I guess you can say. That's why a ds can be changed to a dt, because it's along the curve, along the length of the curve, essentially. Not that it is equal to this at all, but it functions kind of like what a Jacobian would do. If you remember that, it's just basically something you multiply onto your integral, and it changes your, I guess, your parameters, your dimensions. And so it's not a Jacobian. I'm not saying that, but it functions kind of in a way like that, where you're multiplying this I guess this piece onto your original function in a way. And so let's go ahead and just start doing some problems here. So 16.2.002, we got integral over a curve x over y ds. And then they say, well, that curve is actually x equals t cubed, y equals t to the fourth, and we're going from 1 to 4. And that's so nice of them to give us that. I don't think we do that. We don't see that every time. Sometimes we're going to have to create our own, given a picture or just talking about it or something like that. And so, simply put, I'm going to be tossing these things inside of this function or inside of that integral and start getting the answer pretty quickly. But there's one thing I just really want to point out is that, I could toss these in and then I just do the integral. You cannot do that by itself. It's not enough because of the ds. I asked around a while ago. I asked other professors, I said, hey, can you ever just integrate like a ds? And I was told, well, no. You have to convert it. The ds essentially says along the curve, but the curve could be all kind of things. And so we really have to change this into a dt. That's why they're giving us all this cool stuff with t, so that we can actually get the answer. And so what I really need to do is get this arc length kind of formula multiply somethings. I don't really know what you would call it. But I want to take that and get this, I guess, number or function, and I'm going to toss it in with this as well. So let me go ahead and just find that piece on the side. Remember that it's x prime and then squared, and then y prime and then squared. So what are my derivatives of this stuff? Well, it's pretty easy. The 3 comes down, so you got 3t squared squared, and then your 4 is going to come down, so it's a cube now, and then that's still squared. And so we got to, of course, simplify this a little bit here. When you distribute your square, you get 9t to the 4, and here the square will make that into a 16t, and now powers multiply, you're going to get a 6. We could simplify this a tiny bit more by pulling out t to the 4th, which actually on the outside of the square root will make a t squared, thus leaving this behind. So this is definitely not like the end-all be-all that we're going to be working with, but it's definitely easier now that we've done that component. And I'm just going to start tossing stuff into this integral now. So integral is literally equal to the same thing now, 1 to 4. My x over y, I'm going to simply substitute my x and my y, and then I have to multiply by this term. And then dt. Okay. So there's a lot of t's in the front here, obviously. If you put them all together, you got 5 in the top and 4 in the bottom, which is going to make a single 1t on the outside. And this is just right for u substitution. So du, make the 2 come down, you get a 32 dt. And I'm not going to go through all the little nitty-gritty processes, but essentially you're going to, well, we already do the integral here. I have a 1/2, so it'll be 3 over 2. You're dividing by it, so therefore it's a 2/3. And you leave this inside alone. Now it's to the 3/2 from 1 to 4. Okay. So I skipped a million steps there, but it's Calculus 3. This is the last chapter. I'm figuring you can kind of keep up with me a little bit there. Toss in the 4, toss in the 1. We're going to get, obviously, different answers here. I think the 2's can cancel and merge with the 3 to make a 1 over 48. That's going to be a little bit more helpful there. So when you toss in the 4, 4 squared is 16. 16 times 16 is a lot, and then plus the 9. I got 265, and I'm going to call it to the 3/2. And then when you plug in the 1, you'll get 16 plus 9 is 25. Again, now 25 to the 3/2. I think that should be good enough. They simplified their 25 here to a 125 eventually. That's fine, but this should be fine. Okay, next one. So I've got integral over a curve, xy squared ds, and they say that my c is the right half of a circle, and that circle is x squared plus y squared equals 16, and they even say counterclockwise, which is important. So the right half, I'm guessing, is going to be that guy right there, and again, counterclockwise is this right there. My radius will go out until 4. Okay, awesome. Let me pause the video for just a second. All right, so we need a set of parametric equations that are going to make that thing work. I'm going to be slightly preemptive and not just write out x equals this and y equals that. I want to kind of show you some notation that we're going to be using as we keep going. R vector, my R vector is essentially, here in this case, an x and a y. And so I want to put this in terms of t, of course, therefore I can start to do the math for that. And so you can see that we got a circle. I'm going to go back to the polar form of things. My radius is 4 constantly, so I'm going to go 4 cosine of t, 4 sine of t. So that's my r. Again, that's my x and my y. And essentially, whenever you go back to that component that we had in the side here, what you're doing is you're finding the derivative of that r, and then you're finding its magnitude. Notice that derivative and then magnitude. So I'm kind of getting us used to that as we continue on. This is a good notation for sure. So what's my derivative? So my cosine will turn into a negative sine, and then 4 cosine of t. And then I want the magnitude of that derivative. And this is that component that I'm going to toss into the back of my integral to make it work out. So, of course, square root of each of these pieces squared. See how it ends up being the same in the end anyways. And so when you square these 4s, you're going to get a 16, but you can take those 16s and factor them to the front as a 4 on the outside. So that's a 4 on the outside. What you're left with here is sine squared plus cosine squared. Obviously, that negative will go away. So what you have there is a 1, and the square root of 1 is 1. So 4 times 1 is 4. So that's going to be that multiplier put on to my integral. So here we go. My integral up here now is equal to, I'm going to put my limits here in a second. I got x, y squared. Well, x, again, go back here. This is x and this is y. So I got a 4 cosine t, a 4 sine t squared, multiplying it by 4, and then dt. It's that 4 right there. I need to get my limits for t. Notice that we're starting down here and we're working up. I would think that the best is going to be probably negative pi over 2 to pi over 2. That's what I use for my t values. You can think of them kind of like theta values if you like. Okay, so that's my integral that I'm going to do. You could, in a way, use a graphing calculator to just find your integral. Heck, you don't even need a graphing calculator to do integral stuff like this. I can't always promise you that it's actually going to be good in the end, but it might work out. So it is a thought to try. Let me instead do it the long way for just a moment, if that's okay. So notice that we have a 4. When you distribute here, you actually have 2 more 4s. Then you have another 4. That's 4 4s. That's quite a lot. 4 power 4 is 256. And so then I've got sine squared times cosine dt. Use substitution. du is now going to be cosine t dt. This one's nice because it's literally the same thing. So you're going to integrate, you add 1 to the power, divide by the new power. So sine cubed, and then over 3 from negative pi over 2 to pi over 2. Okay. So whenever I plug in a pi over 2 into this, I mean sine or sine cubed, either way, I'm going to get a 1. When I plug in this guy, I'm going to get a negative 1, but because it's the second part of your integral, you're actually going to be minusing it. So what happens is that you got 1 minus a negative 1, essentially. Well, that's 2, and then you put that in here, and you got a 512 over 3. So notice that we actually got a fraction in the end. Could your calculator have done that for you? Probably. I don't want to rely on calculators, but at this point, it's not bad to use them as a tool, especially to make it faster. Okay, so we got integral over a curve, x plus 7y dx, be careful, plus x squared dy. Now this is just completely different, so we're going to have to kind of learn how to make this thing work with us. They're saying that my curve is consisting of 2 line segments. We have 0, 0 to 7, 1, and we have the 7, 1 going to 8, 0. The best thing to do here, honestly, is to make two separate, I guess you can say two separate integrals, two separate integrals, I guess, or paths, and we're going to look at those separately. Let's find our slope from this guy. Y2 minus y1 over x2 minus x1. You can see that we have basically a -1 slope. If I wanted to make this into an equation, let's use this guy. So -1 x minus the 8. And so we got -x and then plus 8. So there's your line equation for that. This one's actually much easier here because you're starting at the origin. So your slope here is going to be 1/7 and then just x, and that's it there. Very simple. So what I'm going to do is say two separate ones. I got y1 is equal to 1/7 x. Sorry, I was just looking at my notation. Was a little strange for a second. Yeah, that's good. That's good. And then I got a y2, which is -x plus 8. So I want to find my derivatives and stuff like that. I'm going to kind of show you why in a second. So like dy for this guy is going to be a 1/7 dx. Notice I'm doing it implicitly. Over here, dy is equal to a -1 dx. One last thing. If I'm going to integrate this, this one's going to be from 0 to 7, and this one here is from 7 to 8. And I'm using x's here because they're kind of basic. I think we all know how to integrate with x. It really makes us feel better about it, I suppose. So, in order to get this problem done, I'm going to rewrite this, I guess, big integral thing using x's. And so instead of using t's or something like that, and you could use t's, I'm going to use x's. Notice that like dx, that's not too bad, but a dy, well, we can plug that in. We can substitute that in and get a dx. So it's kind of like what we were doing last time, but now I guess more just plain x's instead of using t's and stuff like that. So let me show you what this actually breaks down to now. 0 to 7 is my first integral of... I got x plus, and then notice 7 times y. So 7 times, what is y in this case? It's right there. 1/7 x dx, and then plus x squared, and then dy is right here. So times 1/7 dx. So that's my first integral here, I guess you can say. And then the next one, I'm going to go now from 7 to 8. Of basically the same thing, x plus 7 times my y in this case is right here, -x plus 8 dx, and then x squared, and then my dy is going to be a -1 dx. Okay, whew. There is no really getting around the fact that you got two different integrals going on here. That's okay. Let me try to simplify just a tiny bit here. So notice that we have 7 and 7 are going to cancel, and so this right here, I guess I could have done a dx kind of like that. That's probably more proper. We got the 7's cancel, make basically a 2x. So far I got a 2x. Over here, I got a 1/7 x squared, and that's my dx plus, and then the other integral, 7 to 8. Notice again, when I distribute my 7, I'm going to have a -7 plus 1 is a -6x. And my number, I guess you can say, is a 56. And then over here, I got a -x squared dx. What I did, I don't want to call it cheating, but I certainly did not do all that. They're just polynomials. It's not a big deal. So I did my integral in the calculator. I got 196 over 3. And then plus over here, this guy was a -136 over 3. You put them together, and I got 20. Out of all things, I got a 20. So there you go. Keep cruising. 16.2013. Integral over a curve. X, y, e to the y times z dy. Watch out. Watch out for that dy. I had first done this problem thinking it was a ds, and well, you could imagine that the whole thing was wrong, and I did way too many steps when this problem's actually quite easy. So watch out, that's a dy. I have my curve is x equals 3t, y equals 2t squared, z is equal to 3t cubed, and they're saying we're going to go from 0 to 1. Earlier, I was using r, so in this particular case, you would have 3t, 2t squared, 3t cubed. Okay, this is your x, y, and your z. And so later on, like if I were going to use it, I would have my r prime and then my magnitude of r prime. But again, this was not the way to do this particular problem, at least initially, because it's not ds. Again, see, I even got caught up in it again. You don't always have to go through these same steps. Watch out. It's a dy. It's a little different. If you remember from the last problem, what we were doing was I tried to convert this over to like an x or something. Well, notice that we got a lot of t's. So I want to convert that dy into a dt somehow. I'm going to use this guy right here. So let's just, here, I'm going to get rid of all that. We don't need that. I got a y is equal to 2t squared. So dy is equal to what? 4t dt. I'm pretty much, I can plug that in. I can substitute that in here in just a moment. All the rest of the letters also can be just substituted in. I don't see a need to do anything otherwise. So 0 to 1. I got my x was a 3t. My y is a 2t squared. I got e to the 2t squared times 3t cubed. And then, of course, dy is now 4t dt. That's a lot going on. So trying to put some of the pieces together here. I actually got 6 and then a 4. We'll make a 24. Just go ahead and toss that in the front. I got t to the 4th e, and then up here I got a 6t to the 5th. And notice that's pretty much the only way that this could happen is if you did a u substitution. That should help. So u substitution, 6t to the 5th. du is now 30 t to the 4th dt. If you know how this works, you divide by the 30. And then what's your integral of e to the u is e to the u. So you just go ahead and go and replace it there from 0 to 1. Go ahead and plug in the 1 and the 0. Plugging in the 1 will get me e to the 6. And plugging in the 0 gets the e to the 0 is a 1, essentially. So there's your answer. Not too bad on that problem. Next. 16.2022. Because I was telling you about that r stuff, here's now further notation. This is a line integral, it says. Integral over a curve of f dot dr. F dot dr. That's a dot product. So that basically you have a vector, and you're dot producting them. D, this is the Leibniz notation for essentially r prime, right? That's the Newtonian style of saying it. D derivative, you're taking a derivative, so r prime, and essentially like the magnitude like I was originally saying, and you would just put a dt in there. So it's very similar in design, but you can actually and literally follow this with a dot product. So that's what I'm going to do in this case. I'm going to just simply use the dot product, as they say, and that's good. It's a good thing. So my original f in this particular problem is x plus y squared, xz, y plus z. And my r, of course they have to give it to me for me to know this stuff. I got t squared, t cubed, and then negative 2t. And I'm going from 0 to 2 for my t. Okay, notice what's going on here is that this is literally my x, my y, and my z, because it's my r vector. But I also need my derivative, my dr, essentially. So 2t, 3t squared, and a negative 2. This is going to be important to use here in a second. And this is also important, but it's not quite ready. What I need to do is I'm going to go back and put t's in here. Notice that this is x, y, and z right here. I can literally substitute those in and get, like, I guess you could say like f of t in a way. So let me rewrite my f vector in terms of t. So I got x squared. Here I got squared cubed, should be powers of powers multiply, make a 6. xz, so I got a t squared times negative 2t. And then finally over here, t cubed, and then minus the 2t there. I'm going to just simplify it just a tiny, tiny bit. T squared, t to the 6, I like that. Negative t and then a cube. And this guy is fine the way he is. So this is my f vector. And remember my r prime vector. Let me go ahead and just rewrite it. It's a square there. And I'm going to dot product these two. So this is actually the math that we're going to be doing here. I want to dot product them. So integral 0 to 2, as they had told me, of the dot product of these guys. Now, I don't want to keep rewriting this a million times because I know that you can kind of do the dot product very simply. But I'm going to do it just for the sake of the recording. That way you are 100% understanding exactly what I'm doing here. Okay, awesome. So what I did was f dot dr, essentially. So, sorry about that. So I'm going to dot product them. And again, my dot product yields a scalar, not a vector. And so, this times this. So 2t times the t to the 6 plus the t squared. We'll kind of decipher that here in a second. Plus sign. This one times that one. Negative 6t. And then when I'm multiplying them, you're adding the powers to make a fifth. Might as well do a little bit of math there. And then plus this guy times this one. So negative 2t cubed minus 2t dt. Go ahead and distribute. Let's try to make this a little bit better. So then I got 2t to the 7 plus 2t cubed minus 6t to the 5th minus 2t cubed, and then plus 4t dt. Some of these I think will, right here, these guys are going to cancel, so that's a little bit better. And so we're left with this big old integral here. It's obviously polynomial, so you could just use a calculator if you want, but might as well do it right quick. So we got a 2 t to the 8th over 8 minus 6 t to the 6 over 6, and then plus 4 t squared all over 2 from 0 to 2. 0 is going to cancel. 2 is actually important. Here we got a 1/4 times 2 to the 8th. That's kind of crazy. The 6's cancel here. 2 to the 6. And then the 2 is left over here in the front. 2 squared. And at some point you will use calculator and you get 8. So there you go. All right. Awesome. Next question. 16.2.031. So similar thing, I got an f is equal to e x minus 1, and then x times y. My r is equal to t to the 4, and then t cubed. And they're wanting to go 0 to 1. And they want to go ahead and say, what is your integral of f dot dr? Okay. Well, first off, I want to rewrite my f vector. Again, remember that this is x and this is y, right? So I'm just plugging them in as I see. So I got e to the t4 minus 1. Here I've got t to the 4th times t cubed. Just a tiny bit of simplifying here. Multiplying the bases, you add the powers to make a 7. So that's my f vector. Okay, r. I have my original is t to the 4th t cubed. And so then r prime would then be 4t cubed 3t squared. So this one, we're going to dot product them and go from 0 to 1. So here we go. So t to the 4 minus 1, t to the 7. So many lines going on. 4t cubed, 3t squared, dt. So these guys are going to multiply, and those guys are going to multiply. 4t cubed, t to the 4 minus 1, so I'm multiplying those two guys together, then plus 3t to the 9, actually, dt, 0 to 1. Notice that you would use u substitution here and all that stuff. In fact, it is important because I'm looking at the answer and it's not easy to get in the calculator, so let's go ahead and do that. My u substitution says t to the 4 minus 1 du then is a 4t cubed dt. Normally, if you've seen my other lectures, I always do dt, then du divide by this stuff, but we're Cal3 near the end. I'm skipping a lot of steps at this point. Notice that this right here is literally the same here, so I don't even have to do that step. It's a copy paste essentially, so that's good. So I got integral e to the u over on that side du, and then on this side over here, I'm just going to be integrating 3t to the 9th dt. My integral of e to the u is e to the u, obviously. Go ahead and replace it, and then over here, I add 1 to the power, divide by the new power, divide by 10 from 0 to 1. When you plug in the 1, notice that over here 1 minus 1 is 0, e to the 0 is a 1. And over here we're going to get 3 tenths, that's a plus sign between them, minus, and then I plug in the 0, is actually important. Plugging in the 0 here, I got e to the negative 1, so 1 over e essentially. And then over here I get a 0. So my final answer, when you put these two together, that's just 10 over 10 plus 3 over 10 is 13 over 10 minus 1 over e. So I don't think you would have got that from the calculator. It's not something that would have easily come up. Next question. 16.2035. This is that thin wire that we were talking about way earlier. They have a thin wire, and it's going along the x squared plus y squared equals 64 as long as x is greater than or equal to 0. They have a constant density of the wire equal to k. It's constant. And I think that's... What are they wanting here in this problem? They want to know the mass, and then they want to know the center of mass. So let's draw it out first. Essentially, they're saying we got this guy, and might as well do counterclockwise because, well, why not? Again, because x greater than or equal to 0 means it's got to be positive over here, and the radius here would be an 8. Okay. So my r vector, my pathway, would be 8 cosine of t, 8 sine of t. R prime, my derivative would be a negative 8 sine t, 8 cosine of t. So the magnitude of r prime, which I'm pretty sure I'm going to use here in a second anyways, is going to be the square root of this stuff. Basically, if you're thinking about what's the magnitude of r prime, you're looking here and you're trying to find your radius. And it's basically a circle as well, and your radius is going to be simply an 8. So we'll be using that 8 here in just a moment, I'm sure. Yes. So that's really good. That's really handy. Okay. So what are they actually looking for is the mass, which is going to simply be my integral of my density times that dr, yeah, the dr essentially. So 8 dt. I know it's kind of underwhelming. It's not really as much as you were thinking, but you're just simply integrating k. I'm pretty sure that their original would have looked something kind of like that for your mass. But I'm having to convert. It's not ds. It needs to be a dt, and we already had done that portion of it. My t's should go negative pi over 2 to pi over 2. If you're noticing, we had already done a problem similar to that earlier. The 8k can actually come out to the front, and so you do 1 dt. And so you're going to say pi over 2 minus a negative pi over 2. Essentially, that becomes a pi. So 8 pi k is your mass. So they're going to ask for that first. And then they're going to ask for x bar, y bar. Pretty much, I'm thinking it's in a point form, but we might as well do it anyways. It's going to be the same integral earlier, but then we're actually putting an x in there, a new x, I guess you can say. This is all kind of jumbled. You can't actually integrate something like that because you need everything to be in terms of t. Not that the ds would have helped you anymore. I'm just saying x bar, you're going to have an x in there, and eventually you're going to divide by the mass, which, well, we just found a second ago. The k's are going to cancel, the 8's are going to cancel, so essentially you're going to have a 1 over pi, and then integral of x dt. Well, this is not appropriate. You can't actually integrate x dt, but you do know that this was an x and a y originally. Notice that I'm going to plug in my x, and that's in terms of t, making it quite easy. That's 8 cosine of t dt. So when I integrate my cosine here, the 8 can come out to the front. Integral of cosine is going to be a sine of t from negative pi over 2 to pi over 2. Plugging in both of these, you get a 1 minus another one is a 2. So essentially, this ends up being 16. 2 times 8 is 16 over pi. So that's my x bar. You know what funny is about y bar? You could go and do the whole thing with the y in the integral as well. But if you go back to the actual picture, I'm saying, hey, this is my wire and it has a constant density. Where's my center mass for x? Well, we had to go and find that. But where's my center mass for y is right here, right in the middle. The answer is 0. So that's actually really helpful. So I'm pretty sure they're going to want it in point form. And what it looks like then is 16 over pi, comma 0, something kind of like that. Okay, next one. 162047. This one kind of confused me, especially with the words. So we'll just have to kind of work through it here. It was a 180-pound man is also carrying plus 5 pounds of paint up a helical staircase. Helical staircase. Oops. Case. It has a radius of 20 feet. It's 80 feet high. Just high. And there's 2 complete revolutions to get up to the 80 feet, I was assuming. How much work is done by gravity, basically. Okay, so what's going on? Essentially, I'm going to make up a staircase that's going to go up twice. Notice that I had 1 revolution here, then we had another 1 revolution there, okay? So 2 revolutions. The total height is 80 feet, and if you're going to take like a look at the XY plane shadow, it's obviously a circle, and they're saying that radius is 20. So we need to make a set of parametric equations, an R, that is going to somehow make this thing work. Once we have it, we toss in, which you can see right here is going to be basically 185, and then we would get our answer. So this is the confusing part, is trying to make an r that would make this thing work here. So kind of focus just on the xy plane for just a moment, right? Because this is essentially x, y, and z, right? Well, let's just focus right here for just a minute. We're pretty good at making circles. We've been doing a couple different problems. Well, that's going to be 20 cosine of t, 20 sine of t. Okay. Now I just need to find out what my z is going to be. Well, notice that it's increasing linearly. Increasing linearly. So it's essentially a linear function that's going to go up all the way there. And you can kind of say you start at 0 and you're going to go up to 80 in a time of, well, if you did your circle, this right here, this time, I suppose, would be up here at 2 pi. And then as you keep going up here, that would actually now be 4 pi. So you're going from 0 to 80 height, there's your z, in the time of 0 to 4 pi. And so doing a slope here, y over x, essentially, you're looking at it. So y over x slope. This is your slope, essentially. Because you start at 0, 0 is kind of easy, actually. So 80 over 4 pi, and then all times t, because again, linear. When I say slope and linear, I'm thinking, like mx plus b kind of stuff. And well, we just found m, x is going to be a t, and you started at 0, so you don't really need that. Okay, r prime, because we're going to need it, negative 20 sine of t, 20 cosine of t, and of course 80 over 4 pi. The t just goes away. The next step is to find that magnitude. Whoa, actually, what's better? Here's the thing with gravity. Okay, so I was about to just toss in a 185, and it might work. I'm not really going to go down that road because that's not the way to do this problem. Notice that gravity does not work side to side. It's only up and down. So gravity is this up and down motion only. So I'm guessing, like, if in a way, and this is very silly, I don't know if you've ever heard this, but like somebody picks up like a heavy rock or a bag of something, and so they pick it up and they walk around a little bit and they set it back down on the ground, and you're like, oh wow, that was a lot of work. Well, technically you didn't do any work. So just like on the side here, you take a sack and you lift it, and so you're holding this sack up, and then you start walking around, and then eventually you just toss it back down on the floor. Well, notice that it was on the ground, and it was on the ground. You did no work, no technical work. I know you walked around with it, that was great, but and it was hard for us to do, but it was no work in the gravity potential energy sense. So what I'm saying is that your x's and y's, they don't matter. It's only the z component that's actually mattering when you're looking at F, which you could basically say is your force. Now, it's kind of funny, going back, we're talking pounds here. Pounds is a force. So again, only the z component's important. And I'm putting that 185 in there as a force, you can say, in this particular case. So I'm just want to make sure, again, that you're knowing that pounds are a force. We're not talking kilograms. Kilograms is not a force. You got kilograms, and then your force for that, once you apply gravity, it's newtons. Here in the English system, you're already there in pounds, so what was back here is actually slugs. But that's a whole other, that's something else we'll talk about never. So, moving on, no one's ever heard of slugs. Let me go ahead and do this problem. So we're going from 0 to 4 pi, and again, my force, in this case, 185 in the z component, my up and down component, and then my r prime would be that negative 20 sine, 20 cosine, and then, of course, 80 over 4 pi. Again, remember that this was r prime. If I could draw an r, it's r prime. So this is f dot dr, essentially. Like, it's dr, f dot dr. When you dot product, it's actually kind of funny because these zeros here are going to cancel out all that stuff, and so you're just left with this 185 times over here. So 185 times 80 over 4 pi dt, and again it's 0 to 4 pi here. You don't even have a t here, so you just add a t, go ahead and tack on that that 4 pi. The 4 pi's are going to cancel. 80 times 185 is 14800, and now you've done work. This is work, which is now measured in foot-pounds. Okay, so again, pounds was force, work is foot-pounds. Okay, that's the end of this lecture, actually. So thank you very much. Have a great day.